I brought a talk here that part of the intention is to create some discussion, and you're going to see why very soon. So I'm coming from Switzerland, that place there on the map. I'm originally from Sao Paulo. Here is the Italian part of Switzerland, very close to Como, very close to George Clooney, and very close to Milano and all the fashion. Few pictures. This is the picture from my window. Here you can see the city. It's known as the Rio de Janeiro of Switzerland because of the mountains around the lake. And what do I do? So if you can interpret the joke there, I'm a computer scientist. So that's the baby being born and saying the word. What I think you do, well, the windows and doors are open now, so I think we don't have that uncertainty, but let's not look through the door and let's suppose we can see outside. And then we have a detector, and the detector here rolls 2 dice and lies if it gets double 6, and tells the truth in the other case, and is a detector if the sun has exploded. And then we have a very simple calculation here. We play the game, we ask the detector roll the dice and say, yes, the sun exploded, and the probability of that happening by chance is 0.002, 7. So the pragmatist has concluded that the sun has exploded, and I think you have taken the other part and bet $50 or maybe more that it has it. What is this talk about then? I'm the computer scientist talking to audience mostly of statisticians. I came to talk about maximum entropy approach to learn Bayesian networks. Yes, for now, that is really my paper about, but I'm going to insert some other things together with this paper in this discussion. And this is the main takeout of this. So we can have a worse statistical model framework, inference method, or a better one. And with that choice, we can have a worse way to do computations or a better way to do computations. Of course, if you are in the upper left quadrant, you are not doing very well. If you are in the bottom right, yes, that is the goal, but not always that is possible. And I'm going to play with the other two in yellow. So the Bayesian network is, even if the name is a Bayesian network, this is just a model to compactly represent a distribution. Most of the time this is done using discrete variables. I'm going to talk more about discrete variables. So I have a domain with many discrete variables. The many here means a lot of variables. And let's suppose that for a moment they are binary variables, and then I already have to this multivariate. If I would like to write a distribution to explain all these n variables, 2 to the power of n, 3 parameters to play with or to learn to infer. The idea of the Bayesian network is to encode the distribution over all these highly dimensional domain in a more compact way using independence. So independence is the key thing in a Bayesian network, and the idea is we draw a graph and we say that every variable is independent of the non-descendants given the parents in this graph. The graph has a direction. The direction doesn't mean causality. It just means what I just said. So, for example, in this network, the progression status is independent of symptom. It's independent of all the others besides symptom, given the IPE, which is a prognostic index. So this is the idea of the Bayesian network. We are going to use this to encode a joint distribution over all the variables, and we can recover it by using local models, and we can recover the joint distribution by just a product of the local probability distributions, conditional probability distributions that we use in the network. And my goal here is to learn the parameters given that I know this graph. So I know how these variables relate to each other, and I want to learn the parameters of this model, which I'm calling here theta. Theta is the probability of a state of a variable given the state of the parent variables in the network. I want to learn these local models to then build up together this Bayesian network. In this example, I have just 3 variables, and for example, I have a parameter to specify the probability of x1 being on state 1, x1 being on state 2, and another parameter for x2, and then many parameters for x3, because x3 I have to specify it condition on the values of x1 and x2. Some of the parameters here are not really independent if we think that this is binary, so some of them here is one minus the other, but let's ignore this for a moment. So I have many parameters in this case here to specify. This will of course increase a lot if the dimension of if the number of states of each one of these variables is more than 2. In this example I'm using 2. What I have in my hands is a data set. The data set contains IIG samples, but IIG are the lines of this data set, while the columns, so the rows are IIG, the columns, they respect that relation of the Bayesian network that I know. So the dependence between the variables within one of these rows is given by the Bayesian network, which I know the structure. So I have those 3 variables and a list of IIG samples here. They are complete, and this is the first example. And then I can easily compute the log likelihood function. In this case, it's just I just have to play with counts from the data, and I can easily compute. In this example, I have taken the row number 4, which is a 1, 1, 2. Is assumed they are binary, and the log likelihood here is just the sum of these logs of these 3 parameters, which are the ones related to this 1, 1, 2 appearance on the row number 4. If I want to infer a Bayesian network, I can treat this theta as a random variable and use a prior. I'm going to use a conjugate model. I use a Dirichlet prior. I assume this prior to factorize, so all parameters are independent, so this is a product Dirichlet, and I have this product of all these priors over all these conditional distributions over the network. The posterior will again be a product Dirichlet. My data is multinomial, so I have a conjugate model. Everything is easy to compute. If I wanted to absorb a new data, so I want to absorb the data row number n plus 1, given all the data up to row m. Everything I have to do is a very simple computation with the Bayesian inference, and I get just the counts is an update of the Dirichlet, and the counts sum to the parameters of my Dirichlet. The problem that I have is that I have incomplete data, so I don't have a complete data set. The interrogation mark is here showing an example. I still want to learn a Bayesian network, but with incomplete data. I'm going to assume that this data is missing at random. I'm not going to discuss about the missingness process. So I'm just going to go on here in the most common way. In this case, we have still want to work with a product Dirichlet. I still would like to have a conjugate model, work with that. So I still define here my P as that prior as a product Dirichlet. What happens is that I want to absorb one data now. I will absorb a data at a time. And the first data sample that I am absorbing, the moment I do the computations, I have to do the summation over what is missing on this data sample. Okay, so I have a sample of all my n variables, and I have a summation over what is missing. Okay, then I can do the summation because I'm assuming the data to be missing at random. And this is going to be my posterior, based on the summation over the missing values. What happens is that if I keep doing that, so I absorb the first data, and what I have now is not a product Dirichlet anymore, but a mixture of product Dirichlet. And if I keep doing this, every new data that I want to absorb, I'm going to get a mixture of product Dirichlet, which increases with the number of data I absorb. This does not factorize anymore as the initial Bayesian network did. So the prior had a nice characteristic. I could update the distribution layer, just sum the counts, computations were very efficient, and I lost that by trying to do this Bayesian inference here. And in fact, we kind of lost most of the benefits that we have on this model called Bayesian network, because we lost this independence of parameters that we can keep working with it in a very efficient way. So after absorbing any samples, I start now with a mixture after I absorb the first, and the mixture increases up to, I keep multiplying the dimension of what is missing on every data that I end up, and the size now of this mixture is exponential, and it's very quickly exponential because if I have a few variables missing, even if they're binary, this already gives me about 1,000 dimension here on each one of these summations that I have to do. So this, even with a few data, I already have a list here with a mixture with many terms. And I can't compute with that. That grows really too fast. And then you're going to say, yes, but you don't need to do that. Yeah, that's the take of my talk. I want to do exact computations. I'm the computer scientist guy, and I want to find exact solutions. I don't want to approximate computations. So, yes, we could do a different inference. This problem is hard. We could approximate in a very good way, but I will take a different path at this moment, and I will choose not to use an ideal inference procedure in pro of having an easy way to compute with it. So now I'm giving away a full Bayesian inference, and I'm going to step a bit outside that and use a maximum posterior inference. So in this case, I have my incomplete data. My function is still the same. I have my prior and likelihood. And what I want now is to find the theta that is the theta that maximizes my function, which I'm calling here, I will call in the next slides the map score. So I change a little bit the model, so I can do computations in an efficient way. A quick example here. I have a network with five nodes. If these two nodes are missing, then what I end up is with a polynomial programming problem to solve. I have to maximize over theta a function that is a function of summations of logs with the counts from the data. When the rows that data are complete are easy because this factorize, and the rows that data are incomplete, this becomes a summation of a log of a summation inside, and it's hard to compute with. And what I'm going to do is to write a long, but still short compared to that very long mixture of the product usually I had. So I'm going to write a polynomial programming which I will solve exactly. And when I say exactly, I'm not using a package and just running. I'm writing a way that I guarantee that I'm going to find the maximum theta. So the computation, there is no error in the computation here. There might be an error in the model. The way I defined my inference problem, that might be not the correct one, but the computation is exact. So we developed a global solver for this type of problem. This is a very hard problem. The most common way to solve that kind of problem is expectation maximization, which I'm not going to talk into any detail. But the very simple way of seeing is that we complete the data with expectations, and then we do maximization with complete data which we know, and then we take this new theta and complete the data again, and we just do these two iterations and keep doing until convergence. This is the common way. It's not a global way to solve the problem. This is an approximate way, and might just get stuck into local optima. What we did then, okay, let's compare these two things. So now I'm assuming that the model is there, it's fixed. I can't do anything to improve it. Somebody gave me that I have to solve as a computer scientist. So I compared the global solver against EM, which is a very good and very well used way to learn Bayesian networks. So the points here are the KL divergence of the models that I obtained, and which means that if we are above the identity line here, means that the KL divergence of this, which was EM solving the maximum posterior problem, is smaller than the KL of my global solver. So points above the identity means that EM was better than the global solver. And the message here is, okay, EM then was good because it was not good. Because it didn't optimize the function to the global optimum, it did a better job than my global solver that optimized it to the global optimum. So it shows that we really have to take care about how we compute things. Because we define a function to be optimized, and then I wrote a way to optimize this to the full extent, and I get worse than doing that in an approximate way. Which means the function is not ideal. It's the only explanation, otherwise the global solver should be better than the local solver. Okay, so the message is if we use partially unknown computation methods and just run those methods, well, side effects might occur, including better convergence, stuck log optimal running times, errors, rate related to obtain results. Consult your computer specialist before taking a computational method. If you're sure about the result symptoms, but you believe the statistical design is correct, then consult your design and computer scientist or search for advice at CS center near you. And it is also working the other way around. But I'm sorry, I have to say this, otherwise I might be sued. Okay, then. So let's take a more machine learning approach. I have just a few minutes. The more machine learning approach is, okay, let's try to fix that function. I would like to start again from the beginning with the full Bayesian, but I really cannot compute with that. I still want to do exact computations. So what was our fix to the function? We look to the points we generate. These points are points obtained running EM, and we are running EM, not the global solver. We don't need to run the global solver. The EM does a better job. So we run EM many times, and then how dark is the point? As better the KL divergence, means closer to the model I used to generate the data. And here we have the posterior probability, and here we have entropy. So there is a correlation between the two things, the amount of entropy that we have and the probability, the posterior probability. So what we devised, okay, let's change a little bit the formulation. What I'm going to do is I will take the model which has highest entropy, which is can be seen as a measure of conservativeness. So I will take the one with the highest entropy. As long as the score of that network, so the posterior probability is greater than some constant out of the best possible one. So I take the best possible one, which I can compute exactly, and then I put some threshold here and I say any model that is as close as this to the best possible one, I'm happy with. It's sort of a Bayesian factor, but it's not really a Bayesian factor. I'm not using full Bayesian inference, so it's a sort of a Bayesian Bayes factor with maximum posterior probability. And then I optimize this globally. This is a convex function, it's nice, but I still have all those constraints to put here in the model, and I have to solve this very complicated problem, but I still can solve this globally. Our solver does the job, and what I get is this. Now if I compare the original most used way to do inference here, which is EM with looking to the maximum posterior probability, against this method, which is a mix, it's distribution with high entropy, but it's also very high score, very high posterior probability, and then I get better results almost always. So, which means I was overfitting when I was choosing the maximum posterior probability distribution. And entropy is smoothing this out. Here are some results with different networks, and we did a nice empirical analysis, and the entropy always gets a little bit better than using entropy over EM. So one possibility that we have here now that anybody that uses Bayesian network can just take and use is continue using EM as you do. You run EM with multiple starts to avoid local optima. Run that 1,000 times, great. But from those 1,000 points, take the one that is closest to the one with highest probability, but it still has a very high entropy. Play this game. Don't just take the one with maximum posterior probability, but the one that has a high posterior probability and high entropy. And then you do a better job. You already do a better job just than taking the one with maximum posterior probability. And then we continue this analysis with larger networks, some well-known Bayesian networks, Asia, alarm, and random networks. And we are always measuring this, all these graphs, the KL divergence, because we are sampling from distribution that we have. Here is the ratio of medians when we run these many times using different Bayesian, sampling from different Bayesian networks and trying to check the KL divergence of the distributions or the KL divergence of some marginalization of those distributions only looking to a few variables inside my domain. The reason to do that is because sometimes the model, the overall distribution is not as similar to the one I sampled the data, but I'm only interested in most of the cases in the marginal distribution of some variables, so I'm comparing also some marginal distributions to see how the models behave. And we always get better results. Less than 1 here means that the median of ours was better than the median of doing the map. So this is my talk, and thank you.